jump in and do a lab. So before we actually start doing the lab, I just want to kind of give you a rundown on what our plan is for the day and for the week and all of that sort of thing. So first of all, happy National Battery Day. Seemed like kind of a weird national day, but I don't even know.
I thought like battery, like a solar battery.
No, like the kind of thing that powers everything that you have. You're like the one person that would have gone there. I don't even know. Wow. All right, come back. We don't have a lot of time, so come back. Happy National Battery Cell That Powers Lots of Things Day. It seemed kind of like a weird thing, but then I was realizing that everything that we have has batteries in it, which is kind of like recognizing that is kind of interesting. Anyway, today we're going to do a quick warm-up problem and then work on our rotational lab, our rotational acceleration lab that we started yesterday. The goal is to get through as much of that as you can. Just a couple of heads up as we're going through. I put homework up for rotational kinetic energy, which is what we did a couple days ago, as well as for angular momentum, which is what we're going to cover tomorrow. The reason that I bring it up right now is because I want to make sure that you're aware that the rotational kinetic energy material is in chapter 7 or chapter 10, excuse me. Chapter 10 is the energy chapter. So they put rotational kinetic energy in with the energy chapter, and then angular momentum is in chapter 9 with the momentum chapter. So you'll have to look in different spots for those pieces of information and the related homework. I also am going to get you some workbook pages. I don't have them copied yet, so I might not get them to you till tomorrow, but those are coming as well, just as more material for you to have to get ready for the test. Speaking of which, the plan for the week, tomorrow we're going to cover angular momentum. That's the last of the big pieces that we are doing in this unit. That's the last kind of big rotational concept that we've got. Thursday is going to be a review day, and Friday is the Unit 7 test. If you know that you will be gone on Friday, then if you want to take it early, let me know. I can make that happen, but I need to know that you want to do that so that I can make sure I have it done and ready and printed. Otherwise, if you're not here on Friday, you need to take that test on Monday, okay? I can't draw it out because we've got lots of other things coming up, okay? Next week, Monday is our review day, or excuse me, Monday and Tuesday are review days, and then Wednesday is our final over all of what we've done this year so far, right? And then Thursday, Friday, we're going to move on to the next unit because we got to keep cruising, keep on trying, okay? Questions that you have for me about those logistics before we keep cruising? Yeah. Okay. All right. So the warm-up problem is one that I'm going to ask you to sit with your lab group to do. And it is right here. So I want you to take a look and listen before you actually start talking. Okay. So yesterday we started talking about the theory behind the motion that you see with the apparatus. The first thing I want you to do today before we do anything else is in your lab group, determine an expression that will allow you to calculate the system's rotational acceleration. This is key here, using kinematics. So this expression that you get for alpha shouldn't have any masses, it shouldn't have any forces, it shouldn't have any of that stuff, okay? So we're looking at it from a purely kinematic perspective. Remember yesterday we talked about how that mass 1 is moving down, right? It's moving, and that's what we're talking about. That's the acceleration that is related to the rotational acceleration and the data you collected. Once you've got that expression, then I'll let you know that it's fine to go back to a lab station and get started, okay? I also want to say, because I don't want you to miss this, I know that there were some groups last year and there are some groups yesterday and here that were so excited about the physics that we kind of forgot some of the basic principles of experimental science, okay? The dependent variable that we're trying to measure is rotational acceleration, but the thing we're actually measuring is time. I don't care how good you are, I wouldn't trust any of you to get a perfect time measurement on one go. All right? What do we do to avoid somebody blinking or hiccuping or a neuron not firing at exactly the right moment? How do we avoid that error that just randomly happens? What do we do? Yes, you have to do multiple trials. How many is enough? How many is multiple? At least 3. So you do 3 trials, and it's not that you need to do 4 or 5 and that makes you better, right? You don't lean on that, but you're gonna break that pulley that's right behind you, Chance. So scooch it up. Yep, thank you. Okay, so you're going to, I just totally lost the train of thought. Do 3 trials. If you get the same value or pretty darn close to the same value 3 times, then you're good. But if one of those 3 is off, then do another trial. Does that make sense? That's the point of doing multiple trials, okay? Multiple trials is important, but that's not necessarily going to give you enough data because each of those trials are just going to average. How many different individual independent variable values do you need? At least, right? 2 is certainly not enough to set up a line. 3 might be, but if one of them's wrong, you don't know which one. 4 is better. 4 is like your bare minimum. 5 is even better, right? You can actually see a trend when you have more than 4 data points. Does that make sense? Okay. So what I want you to do first is to find your partner. Please sit at these front tables, not at the back lab tables. Get out a whiteboard, figure out the expression for kinematics. Once you've got it, check with me, and then I will give you a thumbs up to say, get started. You need to talk to your people. It's not just you, right?